All right, so I'll just do a few problems from this chapter. 10 amp current flows through the wire shown. What is the magnitude of the magnetic field due to a 0.5 millimeter segment of the wire as measured at point A and point B? Okay. So here's the current that flows, and we'll say the current is flowing through the right, to the right. Okay, and if you stick your fingers in the direction of the current, the field is coming out of the sheet. Okay, so the field is coming out of the sheet. Okay, this guy is producing a field that's coming out. This guy is also producing a field that's coming out, and so on. So we're going to calculate the field due to just this current. And if you wanted to calculate the field due to the entire current, you would add all those, the field due to this guy, you do that integral. Okay. If you look at the expression, the field due to this guy, the magnetic field is a vector field, is equal to mu naught. Mu naught is a constant vacuum permeability, 4 pi I, the current ds cross r hat, divided by r squared. Okay. For this point, that is r hat. For this point, that is r hat. Okay. All right, we already know the direction of the current, so all we have to do is find the magnitude of the current, of the magnetic field. The magnitude of the magnetic field is, of course, mu naught 4 pi I ds. The magnitude of this is the magnitude of this vector times the magnitude of this vector times sine of the angle between them. Okay. For this guy, that is the angle. For this guy, that is the angle. Okay. Sine of that is 90 degrees. That's one. Sine of this guy, we'll figure it out in a second. Okay. Divided by r squared. So for A, theta is 90 degrees. And so the strength of the field is mu naught 4 pi I ds over r squared. And so let's put all these values in. Mu naught is 4 pi times 10 to the minus 7 Tesla meter per amp. Yep. Divided by 4 pi. The current is 10 amps. The length is 0.5 millimeters. I need a little more space. And R, for A, this distance is 3 centimeters, so 3 into 10 minus 2 meters, and then that's squared. All right, so let's calculate the field. So what we're calculating is the magnetic field at this point due to this element of the current. Okay, again, the total field would be, you'd have to sum up all those elements, but we're just calculating due to this guy. Okay. And the 4 pi cancels. Okay. Let's take care of powers of 10. This is 10 to the minus 4. And then 10 minus 3, so that you get 10 to the 1, and then 10 minus 6. So dB, the field at A due to that element is 10 minus 6, and it will work out in Tesla. Okay. And this is 3 centimeters away from this 10 amp carrying current. So a 10 amp current, and you're finding the field an inch away from the wire. Okay. So this is 10 times 0.5 divided by 3 square is 9. Okay. So 5/9 microtesla. About half a microtesla. The Earth's magnetic field is half a Gauss, 0.5 times 10 to the minus 4 Tesla. So this is 100 times weaker. Okay. All right, now we'll again find the field due to this guy at point B. What do you expect for the answer? Will it be equal to that?
Should be smaller, right?
It'll be smaller, okay? But roughly of that order. So we'll see it'll be smaller than this. So let's find that, okay? Now, for the magnitude, now we'll have to use sine theta. Sine theta is this distance divided by the hypotenuse. And what is the hypotenuse for this triangle? For a 3-4 triangle, it's 5. So sine theta is 3/5. Okay, so this will be 3/5. For B. Okay, there is ds, and there is B. The field is coming out of the paper. This is 5 centimeters. This is 3 centimeters. There's theta. dB, the infinitesimal field is mu naught 4 pi I ds sine theta divided by r squared. Yeah. I is 10 amps and ds is 0.5 millimeters. Sine theta is 3/5, and that distance is 5 square, 5 centimeters. All right, so as we had guessed, it should be smaller. The 4 pi cancels, 10 minus 4, so you get 10 minus 6 Tesla, and then what is left? 10 times 0.5 times 3/5, 10 times 0.5 times 3/5, and divided by 5 square, which is 25. Okay, so 3/25. Okay. This was 5/9, which is roughly half, and this is 1/10, roughly 1/10. Okay. So that's the field at that point. All right. Okay, so remember we said that this integral is hard to do. Except for certain configurations. You can do it for a infinitely long straight wire. You can also do this integral for circular loops as long as you're calculating the magnetic field at the center. Again, this integral would be hard to do for any of these other points. If you wanted to find the magnetic field at this point, you're out of luck here, and all that. You can do it where you can calculate the magnetic field at this point. Okay. All right. You might remember from the expression, the field produced by this element at that point is what? Okay. So you saw that the field produced by this moving charge along the axis is 0. Okay. So the field produced by these moving charges along the axis is 0. So the field produced by this guy here is 0. The field produced by this guy here is 0. Okay. The field produced by this guy at this point, we'll calculate that. The field produced by this guy will be in the opposite direction and weaker. Okay. And again, the way to figure this out is, okay, point your fingers in the direction of the current, and the field at the center points in the direction of your thumb. Okay. So this guy will produce a field coming out of the plane. This guy will produce a field going into the plane. So we'll call it B1 and B2. Okay, 1 and 2. They would cancel each other, except that B2 is weaker than B1. Okay, so the net field will be coming out of the sheet of the paper. Okay, so we'll calculate the field due to loop 1. All right, so B1 is, we're doing this integral mu I 4 pi. Okay, here is ds, and here is r hat. Okay, and the radius, of course, is a. ds cross r hat, that's 90 degrees. Okay, and ds cross r hat is a vector coming out of the sheet, but we already know the direction, so it's ds times r hat is 1, and so r square is a squared. Okay, so you see, it's all constant. You're just adding all these elements ds, and that's a quarter of the circumference. So B1, the field coming out of the sheet is mu naught I my Apple Pencil died. Wow. Oh, there we go. All right, so mu naught I by 4 pi, and it's a square is constant. It's just a matter of adding all these elements, which is a quarter of the 1/4 2 pi a divided by a squared. So this is equal to, one of the a's cancels, and we'll do 2 pi, so that's 2, and 4, 8. So it's mu naught I over 8a. Okay. So similarly, you can do B2, and that'll work out to be mu naught I over 8b in the opposite direction. Okay. So the net magnetic field is B1 minus B2 equal to mu naught I over 8, 1 over a minus 1 over b. Okay. Again, we could do this integral for this shaped conductor only at this point. And again, you saw that the integral was really not that hard to do. Okay? Okay, so this problem asks the magnitude of the magnetic field 50 centimeters from a long, thin, straight wire is 8 microtesla. What is the current through the long wire? Okay. Okay, so what will be the direction of the magnetic field? It's concentric circles. Okay. And so, and mu naught, B is given by mu naught I over 2 pi r, where r is the distance. Okay. All right, so they give you, so they're asking you to find the current. The current is B times 2 pi r divided by mu naught. So B is 8 microtesla. Two pi r is 50 centimeters, and mu naught is 4 pi into 10 to the minus 7 Tesla meter amp. Okay, so you see the units Tesla meter, and you'll get amp at the top. Okay, 2 pi, that's 2, cancels, that's 4 divided, that's 4, and then half, that's 2, so 20 amps. Okay, so the current is, you see a 20 amp current, which is a large current, is producing only a micro Tesla field half a meter away. So 20 amp current is producing a field that is 100 times weaker than the Earth's magnetic field. Okay. All right. A long straight horizontal wire carries a left to right current of 20 amps. If the wire is placed in a uniform magnetic field of magnitude 4 times 10 to the minus 5 Tesla, so this is the Earth's magnetic field, that is directed vertically downwards, so near the poles. So here in this room, the magnetic field is like that. If you go near the magnetic poles, the field will be pointing like that. Okay. That is directed vertically downward. What is the resultant magnitude of the magnetic field? 20 centimeters above the wire, 20 centimeters below the wire. We'll just do one part. Okay, so a long straight horizontal wire carries a left to right current of 20 amps. Okay, so let's find the field below the wire. What direction will the field be below this wire?
Make out of the paper?
Into the paper.
Oh, down there,
Yeah,
yes.
okay, it'll be into the paper. Okay, and this, the strength of this field due to the wire will be mu naught I over 2 pi r, okay, where r is this distance. All right, if the wire is placed uniformly, so the field is there, so this is, oops, that's the field due to the wire, and this is the field due to the Earth's magnetic field. What is the magnet? So this is the external field. Okay, now let's look at it sideways. So there is the field due to the wire, and there is the external field. Okay, they're perpendicular to each other. So this external field is 4 into 10 minus 5 Tesla. Okay. Let's calculate the magnitude of the wire, magnetic field of the wire. Okay, mu naught I is 20 amps. Two pi R. Okay, so 4 pi into 10 minus 7 Tesla meter amp. Current is 20 amps. 2 pi, and R is 20 centimeters, 0.2 meters. Okay, so you get 2 from there, 10 minus 6, uh, 2, the 2 cancels, 20 times 10 minus, okay, so 20 times 10 minus 6 Tesla. Okay, so this field due to the wire is 20 times 10 minus 6. This external field, which is the Earth's magnetic field near the poles, is that. So the net field will be somewhere like that. Okay? And what is the magnitude of the resultant field? So the net field will be in this direction, and the magnitude of the net field is B wire square plus (20) square plus 4 square. That's 416. Square root of 416 is 20.4 into 10 minus 6 Tesla. Okay. And similarly, if you can do it on the top. Okay. All right, we'll do maybe 2 more problems or 1 more. We'll see. All right, this problem says 2 long straight wires are parallel and 10 centimeters apart. One carries a current of 2 amp and the other carries a current of 5 amps. Okay, so you have, if the 2 currents flow in the opposite direction, part A, current flowing in the same direction attract each other, and current flowing in the opposite direction repel each other. Okay. What is the magnitude and direction of the force per unit length? So that force per unit length, the force on this wire per meter of the wire, that's what this expression is. Okay. And what is the force per unit length of this wire? This is the expression for the force per unit length on this wire. What is the force per unit length on this wire?
Would be the same thing but negative?
Yeah, equal and opposite. Okay, Newton's third law. So that's why we. Yeah. 2 pi r. Okay. So force per unit length is given by 4 pi into 10 minus 7 Tesla meter amp, and the currents are 2 amps and 5 amps. 2 pi, they're 10 centimeters apart, 0.1 meter. So you get 2 there, 10 minus 6 again. So, and 5 times 2 is 10. So 2 times 10 is 20. 20 into 10 minus 6 Tesla. No, not Tesla. Newton per meter. Okay, so 20 micronewton per meter. I guess that's roughly the weight of a hair, one of your hairs. Okay, so that force is very small. we'll do one more problem. Okay, a flat circular loop has 20 turns. The radius of the loop is 10 centimeters. N is 20 turns. I is 0.5 amps. Determine the magnitude of the magnetic field at the center of the loop. So they want you to find the magnetic field at the center of the loop. What will be the direction of the magnetic field? How do you figure it out?
Pointing straight up.
You're pointing straight up. Point your fingers in the direction of the current, and your thumb points in the direction of the magnet. So the magnetic field will be pointing straight up. And if you go along the axis, you have an expression, and it falls off rapidly. Okay? So here's the expression. In fact, we'll go look up the expression. There's the expression. Okay? So for a loop, R is the radius of the loop, and Z is the distance along the Z-axis measured from the center. Okay? So mu naught Ni R square. Yeah. So the magnetic field is mu naught Ni R square over 2 times R square plus Z square to the power 3/2. Okay. Ni R square plus Z square to the power 3/2. Okay. So what is Z here? Z is 0 for us. Okay. So the magnetic field at the center is mu naught 4 pi into 10 to the minus 7. N is 20, I is 10 amps. R square, R is 10 centimeters, 0.1 meters square. 2.1 square to the power 3/2. So this is 0.1 cubed. Okay. So this is 0.1 cubed, that is 10 to the minus 3. That makes it 10 to the minus 4, and then 10 to the minus 6. Okay. So that's 10 to the minus 6. 4 pi times 200 divided by 2. Okay. So 2 pi times 200. So 1.26 into 10 minus 3 Tesla. Okay. The Earth's magnetic field is about 0.5 times 10 to the minus 4 Tesla. Okay, so this is 12 times 10 to the minus 4. So about 25 times the Earth's magnetic field. So you see, you want a stronger magnetic field than the Earth's magnetic field, you just get a bunch of loops. And the current is only 0.5 amps. Okay, so, all right, guys. All right, we'll stop here.